Hey, today we're going to look at the magnification and Lensmakers equation, two equations that apply to curved lenses and curved mirrors. So let's jump right into it. This is the magnification and Lensmakers equations. Let's start on the left here with the magnification equation. So the magnification equation really is best understood by looking at just this part of it. So you can see there's really two parts. One that says magnification is HI over HO. In this part of this, HI is the height of the image. HO is the height of the object. So just to kind of understand where this is coming from, imagine that we take an object and the height of the object in real life when we see it is only 1 centimeter. And we use a lens, maybe like at the movie theater, they use a lens to project a 1 centimeter image, but they want to make it much larger. They make it 100 centimeters. We can see then that the magnification is really just the height that we produce of the image, 100 centimeters divided by the 1. In other words, we've made this image 100 times bigger, so our magnification is 100 times. So that's just a simple example to show you how the magnification equation really comes about by this idea of how much really bigger are we making something compared to what it started out as. Now, the magnification equation, again, it has two parts to it. It's got this part that says it's HI over HO, but it turns out that that's the same ratio as DI over DO. So it might be a good time to take a look at what all the different quantities are in these formulas. I'll start at the bottom. In the magnification equation, HI is the image height. HO is the object height. We've already talked a little bit about this. Now, DI is the distance between the image and the lens or mirror, whereas DO is the distance between the object and the lens and mirror. So let's imagine, let me just do a real quick sketch if I can. Let's imagine that I draw a principal axis here, and maybe I'm using a lens like this one to produce an image. And let's say I put my object out here. Here's my object. And let's just do a real quick ray diagram and imagine that a ray of light that comes in parallel goes through a focal point right here. Let's imagine that a second ray of light goes through the geometric center of this mirror, and we end up with an object that is produced somewhere around here. So I'll just draw the object. It'll give us a discussion point. So if this is where, my image is produced, and that was my object, and here's my image, then the distance to the object is measured from basically the center of the device, in this case, the lens. This would represent distance to the object, DO. On the other hand, if we want to measure the distance to the image, we would measure from the center of this lens to where the image is being produced. That's the distance to the image. So, and just to finish this up, this would represent the height of the object. This would represent the height of the image. So you can see the ratio of height of the image divided by the height of the object is the same as the ratio of DI over DO. Now, I'm going to just ask you to put on hold any thoughts in your brains about questioning why this negative is here. We'll get into that in a minute, but the negative is really there for a purpose. And when we dive a little deeper into the magnification equation, you'll see what I mean. But for now, magnification is basically HI over HO, or it's negative DI over DO. Let's take a look at the Lensmakers equation then. So Lensmakers equation gets a little more interesting. It says that 1 over F, where F is the focal length of the mirror lens, 1 over F is equal to 1 over DO plus 1 over DI. So from an equation point of view, really just the three variables, it relates DO and DI. The only thing I'm going to point out before we go too far with this is, number one, there's sometimes a temptation to say, well, if HI over HO is the same as DI over DO, maybe we can get rid of DI here and make it HI, and we can get rid of DO here and make it HO, and that does not work. So do not ever replace that. That actually, that would be disastrous if you did that. So don't change the equation. The other thing some people say is, well, hey, how about in math class where if I take the reciprocal of this, so 1 over f, instead of 1 over f, I'll put f, and then I'll inverse all these things. So f is equal to dO plus di. All I can say to that is it is mathematically wrong. And your first clue is they put this in this form on your data sheet. So don't you think somebody before you would have said, hey, wouldn't it be easier to write it as f equals d over di? Nobody did, because mathematically it doesn't make any sense. It doesn't work. You can convince yourself of that. So this is, in the end, the magnification equation and the Lensmakers equation. And these are really the two equations that govern curved lenses, curved mirrors, and you'll see that we either use one or both of these to start to quantify information about the relationship between the image and the object being produced. Now, if the equations were not enough, there's also something we call sign conventions. And I liken this to when you do vectors, you always have to be careful about direction when it comes to vectors. Well, with Lensmakers equation and magnification equation, you always have to worry about the sign conventions. People in my class, if you take a look at a textbook or anybody that goes out on the internet, you'll find people approach this different ways. For example, our textbook will take a look at separately sign conventions for mirrors and sign conventions for lenses. But I like to deal with these things kind of together, and I think I have a way that does it. But if you don't like the way I summarize my sign conventions here, feel free to take a look at how the book does it. It does it just like I say, it looks at sign conventions of mirrors separate from lenses. You be the judge of how you want to do that. But basically, we have a few quantities that either could have a positive value or a negative value. So those quantities are f, focal point or focal length. We also have in our equations di, we also have do, we have hi, and we have ho. So I'm just going to make a chart here. And on my chart, I'm just going to summarize my sign conventions. Again, we always have the choice to determine if something is either positive or negative. So on one side, I'm going to put when is it positive, on the other side, when is it negative. This is probably going to be incomplete. You can fill it in a little more later, but for a starting point, focal points are positive when they are real. So if you have a lens or a mirror that takes parallel rays and focuses them on a real focal point, we will make that positive in our equations. And then you'll understand the next one. Obviously, if they are virtual focal points, they're negative. Now, if you want, you can go back and take a look and see what lenses and what mirrors have real focal points, and you can put that in here if you like, but I'm going to keep it simple. I'm just going to say if it has a real focal point, it's positive, virtual, it's negative, and then you can take it from there. The distance, well, let's start with the easy one. Distance to the object, we always consider this positive. Right? So we'll always put the DO, the object, on the positive side of the lens or the mirror. It is never negative. And likewise, down here, the height of the object, we will always draw the object in a positive way. We will never look at negative heights of objects. Now, I guess somebody might argue that and say, you know, you could change those, but for me and for our purposes, we're just going to go with that. So that leaves us with DI and DO, or DI and HI. DI is positive whenever we get a real image. I'm going to leave a little spot here because we can talk about what else might happen. But for now, if your ray diagram shows you, and this is why I feel ray diagrams are really important. A lot of people just want to think, oh, why don't we just calculate all this stuff? It's because ray diagrams will give us a pretty good sense of what we can expect for the signs and overall impression of what we'll get for an image before we do any calculations. If the image itself is virtual, not the focal point now, but if the image itself is virtual, it would be a negative one. When it comes to HI, it's a little easier. If it is erect, so when you do a ray diagram and you end up with a positive height to the image when the image is above the principal axis, then we'll say HI is positive. If it is inverted, HI then is negative. And that kind of, I guess, makes sense if I drew a quick ray diagram here and said, let's say I draw a ray diagram for a convex mirror. First ray hits here and bounces off in this direction, so we trace it back to the focal point back here. Second ray heads towards the center curvature and bounces back this way, so we trace it back here. When you get this image over here, you can see, although I've drawn it small, it is erect, so that would mean that it is a positive HI, and that makes sense, it's upright. But we see here that it's a virtual image, so DI is negative. So one of the things I'll point out, and as you get better at this, you'll start to see it. If you do enough ray diagrams and you get enough experience with this, you'll notice that when it comes to DI and DO, you always end up with, when it comes to the image, if DI is positive, HI will be negative and vice versa. So we could put it this way, only one is negative at any given time. So if you notice the quick little ray diagram I drew here, this virtual image has a negative distance because it's virtual, it's behind the mirror, it's negative DI, but it's upright. So DI is negative, HI is positive. If I did a quick ray diagram, let's say of a concave mirror producing an image like this, let's imagine that that goes that way. Let's say that's twice my center curvature, so this goes like this and back this way. So I end up with a real image here. So in that case, DI would be positive, but HI, it's upside down, so it's negative. So keep this in mind, I guess, when we do these calculations in the end of HI and DI, the two things that could be positive or negative, at any given time, one will be positive and one will be negative. Now, there's a million little things like that that you'll start to notice as you go through these things. But at first, this chart will kind of lead us in the right direction. We'll do a couple questions now, and you'll see what I mean. All right, let's take a look at an example question. A 20 centimeter tall object. Let's just highlight some of the key points here. A 20 centimeter tall object is held 10 centimeters from a convex mirror. If the focal length of the mirror is 5 centimeters, what is the magnification of the image? So you'll notice that I'm highlighting the numbers, but definitely you want to keep track of certain key pieces of information because sometimes the description of, for example, the mirror will tell us a little bit about the focal point of the mirror. In this case, it's a convex mirror. So one of the things I would strongly suggest, and if I do my solution here, we can kind of make some notes over here, but you might want to just sketch this situation as you go. So it's a convex mirror, so that would be a mirror kind of like bent this way. We put a 20 centimeter tall object in front of it. So in that case, my height of my object is 20 centimeters. So that's the height from here to here. It's held 10 centimeters in front of the mirror. So from here to the mirror, that sounds like they're describing to me the distance to the object is 10 centimeters. And it's a convex mirror. So as I'm going through, if I draw this out, I start to get a sense of whether or not things are positive or negative. Not a big mystery. HO we said was always positive, DO is always positive, but we confirm that with our picture. Then they say the focal length of the mirror is 5 centimeters. So here's my focal length measured from the mirror to here. And they say it's 5.0 centimeters. But because I drew this quick little ray diagram, I see right away, I need to be careful. The focal point isn't simply 5 centimeters, it's negative 5 centimeters. So I have a negative 5 centimeter focal point. So if I summarize what I'm given in this question, HO is positive 20.0 centimeters. DO is positive 10 centimeters. And the focal length, this is the one that the description really is what we need to pay attention to, and maybe a diagram for ourselves. The focal length is negative 5.00 centimeters. And if you don't catch that, that's a big problem. So pro tip here, read the question, identify values for sure, numbers, but also pay attention to the description of the type of mirror or the type of lens that we deal with. So given all that information, we're really trying to solve the magnification of the image. So when we're done, our final calculation is going to be for magnification. I'll write it down here because I think I know what's going to happen here. We want to either say magnification is HI over HO, or if we can't do that, we'll do negative DI over DO. So that's where we want to end up here. But notice that we don't have enough information. We don't have HI and HO, and we don't have DI and DO. And so you'll get used to this kind of pattern. This is where they're going to force us to do the Lensmakers equation first, get enough information to solve for the magnification equation, and then do that second. So we'll go ahead and do that. 1 over negative 5.00. Oh, probably haven't mentioned this, but you'll notice that I'm not changing this to any standard units like meters or anything like that. And that's because with these equations, as a lot of physics equations, as long as our units are consistent, then we can work in whichever units we want. So if I keep my focal length and my distance to the object in centimeters, then my answer will be in centimeters. So 1 over 5.00 centimeters is 1 over DO plus 1 over DI plus 1 over 10 centimeters. It's always a good idea to put your units and also the sign convention for this as well as you're going through. All right, let's give myself a little bit of room here. Erase my magnification equation. So careful with the calculator, but you should be able to calculate in the end what happens or what DI is. I'll just rearrange it real quickly. So if we do this, 1 over DI is equal to 1 over negative 5.00 centimeters, subtract 1 over 10 centimeters. So I just kind of subtracted this over, flipped them over a little bit. Try it out for yourself. I'm sure you can get to the same place. And so now you can certainly take out a calculator and see what it tells you in terms of the fractions. I'll just do this one. I guess because they're nice round numbers, I can do it this way. 1 over DI is equal to 1 over 5 is the same as 2 over 10. So this is like 2 over negative 10, subtract 1 over 10. So if I take 2 over negative 10, that's like negative 2/10 minus 1/10. That's like negative 3/10. So if 1 over DI is negative 3/10, then DI is 10 over 3. So DI is equal to 10/3, and 10 divided by 3 is 3.33. Don't forget about the negative sign. But again, grab your calculator, go ahead and try it out, and you should get the same value, negative 3.33 centimeters. So that is my distance to the image, but not my answer yet. The answer, or the question, really asks what's the magnification. So the magnification then is, we'll use this form of the equation, negative DI over DO. Don't drop the negative thinking, no, I can cancel it or anything like that. That negative is part of the equation. So when we're done, we have magnification is this negative sign, which is part of the equation. DI is also negative, so we put a negative sign there, 3.33 centimeters. And then we divide the whole thing by DO, which is, DO is 10 centimeters. All right, so the magnification is going to be positive. There's a negative here and a negative here. So those will cancel out, so we get 3.33 divided by 10. So that's going to be 0.33 positive 0.33, and I think we only have 2 digits if we take a look at the 10 centimeters. So we'll call it 0.33 magnification. And so this is a good example then. When we're done, the centimeters cancels out, and magnification really is just a value that is got no units to it. So if you look at this number that we ended up with, basically we're going to magnify this thing to the point where it's actually smaller. It's only 0.33 times the original height, about a third the original height. If I go back to my diagram here, you could probably get a sense of that if you kind of, even quickly, like I'll do right here, did a ray diagram. I'd say, okay, there's my first ray, comes in, hits the mirror, bounces away from the focal point. Second ray heads towards the center curvature back there somewhere and bounces back this way. So we trace that back. And you can see I'm starting to get an object here, sorry, an image being produced that is smaller, magnified to 0.33 the original height. It's got a negative distance and all that is consistent with this question. So, you know, in summary, I'm going to really tout the bonus or the advantage of being able to do ray diagrams really quickly, like I'm doing right here. I don't have to do them. I haven't pulled out a ruler or anything like that. I just did them really quickly. Why? Not to answer the question, but to certainly make sure I'm on the right direction in terms of my quantities that I'm given in this question, and get a sense of what kind of answer I should be expecting. And then notice this, not only is it about a third the size of the original, it's also positive, which means it's erect. So just like when we deal with vectors, where the positives and negatives are very important and sometimes very informative, same in these equations. The positives and negatives are not just some mathematical, you know, tricks. They actually tell us something about the numbers that we're dealing with. So not only do we know this thing's about a third the original height, but we also know that it is erect. So that's a real quick introduction into the Lensmakers equation and magnification equation. One example. These questions really do take practice, and at first they're a little frustrating. Mostly because of the sign convention thing. It takes a little while to get used to always paying attention to your signs and making sure you're getting them right. But one last time, if you can do a ray diagram, if you understand how to do ray diagrams, it really helps you get started. These questions really helps you to scrutinize your answer to see if your answer is correct. So, you know, I'll leave it at that for now. Take a look at a couple of questions, see how they go. But you really, I think this falls into the category of things that you have to kind of try and fail and see the little nuances of questions until you finally get comfortable with them and get better at them. As they say, practice makes perfect.